Hey everyone, Aaron here from Saturn Cloud, and we've got a super exciting video for you showing a full end-to-end data science pipeline on Saturn Cloud. Now we're talking loading terabytes of data, analyzing and processing that data, then deploying a dashboard, and then training a whole bunch of machine learning models and deploying those as REST APIs. Let's get started. Here's a summary notebook that we have, and so there's a GitHub. You can check the link below. All the code from this is available. You can run all of this stuff yourself, and if you want to sign up for Saturn, you can run all of this stuff within Saturn Cloud. And we're using publicly available New York City taxi data. It's a pretty large data set, 1.6 billion records. And this is a good overview as far as what our pipeline is. So like I said, we're processing a bunch of data, we're loading that, cleaning it, and then creating some data sets to do our analysis and the machine learning model training. And then the analysis part is doing some visualizations, and then we can deploy that directly into a dashboard that's live, ready for people to look at. And then we'll do a whole bunch of machine learning experiments and show how using Saturn we can make these experiments a whole lot faster by launching Dask clusters that are managed, and then by launching GPU machines and executing with Rapids and Dask together to parallelize that GPU model training. And then from there, we can deploy those models with the REST API all deployed on Saturn, and then I'll show you a cool example of how the dashboard actually hits that API to do live predictions. So the first thing we're going to start off is with the shiny part, which is the dashboard, and then I'll go into Saturn and show you how all these pieces hook up together, and then we'll run through a few notebooks of the machine learning experiments and some of the different timings by using different tools, and then I'll show you how we can actually deploy these two things, which is the dashboard and the model API, and see how that all interacts together. So let's get started. So we'll start off with the dashboard. This is a really cool visualization built with open source plotting tools like Bokeh, HoloViz, and Panel is what's hosting the dashboard. And then it's deployed within Saturn Cloud, but we'll get to that in just a second. Just to look at the data, it's pretty cool to take a look at this stuff to see almost $4 billion in fares collected and 300 million rides taken over a few years in New York. We can see which zones tend to have the most rides. So Midtown Center in Manhattan had 11 million rides and the average fare was $12. And what's cool is we can actually click on one of these zones, and the heat map on the side here filters so we can see how the rides are for that particular region, you know, how they change over weekdays and then how they change over times of day. So in this particular region, we see that weekdays and in the evenings are really heavy. We can also swap this over to see the fare distribution, to see, you know, what's the average fare for this particular zone on these times. And so it's kind of cool because you can see that the volume peaks at different times of the day versus the actual fare amounts. We can see other places like airports and try to get an idea of how this stuff looks. So this is a really cool interactive visualization that we've set up. And then we're going to jump here into looking a little bit more deeper into the data around tip percentage. So we're looking at, you know, a rider gets charged for a particular ride and then they choose to tip the driver. We want to see, okay, what makes tip percentages higher, you know, because that results in happier drivers, better service, and things like that. What's interesting is this longitudinal view at the bottom is we're looking at, in this case, a 7-day rolling window of the average percent tip. And we'll see tour right here, which is a time at the end of the year. So this is December 31st, January 1st. There tends to be a really, really sharp drop in the tip percentage. And then again, end of November. And then again, early September and early July. And if you're kind of following this pattern, that is major holidays. So New Year's, Thanksgiving, Labor Day, 4th of July, we see a huge drop in tip percentages, which is really interesting, maybe related to tourists, maybe related to locals not being around. So that's pretty cool. And we're going to take this kind of tip percentage idea, and that's where we're doing the machine learning models. So we're building models that can predict the tip percentage based on attributes of a particular ride. So the pickup destination, the drop-off destination, the time of day, the number of passengers. So you can try to get an idea of, okay, how much is this rider potentially going to tip? So when we're looking at this kind of live prediction type thing on the bottom left, this is where there's a model hosted with a REST API, which we'll get into in a second. But we can click a couple zones here in the map, and let's create some hypothetical ride that's happening today at 1 p.m. And once you click predict my tip, you actually send the data back to the REST API, it hits that API, and then the prediction comes back, all hosted here within Saturn. Maybe we'll change the drop-off location to somewhere where we might think the tip percentage could be higher. So we'll go into Midtown, early morning. Maybe this is a ride of somebody going into work. Maybe they do it a lot. That percentage is a little bit higher. So that's pretty cool. We can see how things change, and we can see the different performance of the models here. So you can go ahead and get this on GitHub. You can launch this dashboard yourself. I'm not going to spend any more time here because now we're going to dive into the mechanics of how all the stuff happens, how you can analyze the data, build the dashboard, build the models, and all that stuff. So here we're within Saturn Cloud. Our starting point is our Jupyter servers. These are the workspaces for us to actually launch up a Jupyter notebook and get going and start coding. The key components of these servers are the machine that you're using, so the Amazon instance type. In this case, on the left, I have a pretty big machine that has 200 gigs of RAM. And on the right, I have another one that has a GPU on it. And we're going to do different things on each of those. Another key component is the image that you're using. So what you do with Saturn is you supply the packages that you would need to do your work, and then Saturn builds and hosts that image for you. So when you launch the Jupyter server, everything is already configured and ready to go. But even more importantly, if you were to launch a Dask cluster with tens or hundreds of machines, all of those machines have the same configuration, the same packages on them. As well as when you're ready to go and deploy this into a dashboard or a model, it's using the same exact image, and then it's pulling your code right from here within this project. And I'll show that in just a second. But we'll take a peek at the image that we have. The actual Conda environment file is on GitHub for you to see what packages we used. We load this up into Saturn, it builds it, it's ready to go. And now we can jump into JupyterLab and do the work that we need to. So this is actually the screen that I showed you before that has a summary loaded. I'm inside this machine that has 200 gigs of RAM. And we have a bunch of notebooks here that are doing different things. We have an ETL notebook that pulls down these CSV files and then writes partitioned Parquet files, and then an ML dataset notebook that creates the dataset. So I'm not going to go into all of these components. You can go check out the code yourself, but I'll just show you a quick overview of what we're doing for the machine learning. So this is our dataset. We have a few features here about pickup and drop-off locations, and then some stuff about time of day. And then the thing that we're predicting is the tip fraction, or the tip percentage. So how much of the fair amount did the rider tip? And we can see the distribution of this data. It's around 22% is the average, median's around 24, and some people are really generous, tipping a lot. So we're training models that are going to predict this particular number. So to give you an overview of what we did and what's available in the GitHub is right here. I'm not going to run through all of these right now in the video. I'll show you one quick example, but we trained linear models and did some hyperparameter tuning with them. We did XGBoost, and then we also did random forest. And then to get an idea of really how much faster it is to run stuff on Saturn using Dask and Rapids clusters, we did some comparisons to single node scikit work that you might be used to on your laptop. And then we also did things outside of Saturn on a Spark cluster and did some benchmarks just to see how that turned out. If you're not familiar with it, Spark is another popular cluster computing framework. It's written in Scala, it has a Python API, but Saturn here manages Dask and Rapids clusters, which are Python native parallel computing using CPUs or with GPUs, and you'll see how it's a lot faster. So here's one example of where we have a hyperparameter tuning thing with scikit-learn. So this is just regular single node Python. We are doing this on a pretty hefty machine with 200 gigs of RAM, but we're doing a grid search with a smaller sample of the data just to kind of illustrate it. So in this case, we'll set up our scikit-learn pipeline. We have a grid here, which I'll show you what that grid looks like. It's around 400 items. This is that grid, and we just have this in a helper file because it's going to happen in a few different places. So we'll do that. We set up our grid search, and I actually have it running. I kicked it off before I started recording. And this is actually, since we're using this njobs equals -1, we're parallelizing this grid to all of the cores on the single node. So we're still just using regular scikit-learn, but we can see here that all of our resources are being utilized. So this is using almost all of the 250 gigs of RAM. All of the cores are executing. So this might take a while to run. I'm going to kind of kill this and show you a completed example because it does actually take quite a long time, a little over 2 hours. And we have another video that does a deep dive into this hyperparameter tuning exercise, so you can check that out on our YouTube channel as well. So what I want to show you though is a comparison of this particular scikit-learn one and how easy it is to translate that into running on a cluster with Dask. So really don't have to change much code because Dask is a Python native parallel computing framework. The data frame API looks a lot like Pandas. The machine learning API looks a lot like scikit-learn and actually interacts with scikit-learn, as we'll see. So the difference here is we're not just using one machine with 200 gigs of RAM, we're using 10 machines on a cluster. And with Saturn, you can import our Saturn cluster object, and then that initializes and manages the Dask cluster for you. So in this case, we asked for 10 machines. We now have over 2 terabytes of RAM running. And remember, this has all of your packages, the image that we created up front. Now all of these machines are good and ready to go. So the data loading looks very similar. And then here we'll jump down to the grid search code. And so we'll see that we're actually still using a scikit-learn elastic net class, because the data is pretty small. What we're doing here is we're parallelizing the computation of the grid search. And the code looks very similar, same kind of API for grid search. And then we'll see here that it only took 1 minute. So I'm going to kick this off just so we can see kind of what's going on behind the scenes. So now I'm running the same exact grid search, but I'm doing it with Dask on a cluster. So if I go back to my terminal here, I see that now on my client, which is my Jupyter server, nothing is really running. All my resources are kind of free because nothing's actually happening on this node. It's all happening in the cluster. And so we have a Dask dashboard UI kind of hooked up where you can click that and you can see what's happening. So this is really cool because you can see all of the different functions that are executing in parallel across the cluster. We see that our CPUs are doing a lot of processing, whereas we're not really memory bound for this particular example. And we can see that there's 1,200 different elastic net fits that are happening in the background. So that's pretty cool, right? We wrote a scikit-learn pipeline. We can translate that into Dask running on a cluster in Saturn pretty easily. The next example I want to show you is a Jupyter lab that's hosted on that GPU instance that I was showing you. Similar idea, we did a scikit-learn random forest, and then we took that onto a cluster on Saturn. But the difference here is that we're using a GPU cluster and we're using Rapids with Dask to do the parallel GPU training. So here I now have a different size cluster that each has a single NVIDIA GPU on it. And I did the random forest training on this single node scikit, and that took 10 minutes. But this data size is a lot larger than the one we saw before. We're doing 200 million records. So we're training a random forest on 200 million records. That's quite a lot that's going on there. We run this, and we see that the API is, again, very similar between the scikit-learn and the Dask Rapids one. And this one just takes 1 second to run the same exact training. And there it is. That's it. So we also have another video going deeper into this random forest comparison. We compare it to Spark 2 and show that Rapids is a whole lot faster. So check that out too. Okay, I'm back to my CPU machine, and we're going to just give a quick overview again on the machine learning that happened. There's a whole lot of other machine learning models. Like I said, we did XGBoost, and we did that, compared it to Spark and random forest and a lot of different things. So I just want to go through a quick overview of that, and then you can dive into the code yourself and see the specific runtimes and the specific implementations of everything. So what I just showed you now was this elastic net hyperparameter tuning example. The scikit-learn one took just over 2 hours on the single node. Spark, we have a notebook included that took 47 minutes, and then Dask took 1 minute. So that's Dask on a cluster in Saturn, 100 times faster than the scikit one, and then over 40 times faster than Spark. We did the same thing with XGBoost, running a single node on scikit. XGBoost has a scikit-learn wrapper, even though behind the scenes it's not actually built in scikit, but just for this comparison, we're referring to scikit as the single node Python. In this case, it took almost 3 hours to run. And then just with Dask, basically launching a cluster, running almost the same exact code, we can reduce that time down to 10 minutes. And that's 15 times faster just with a couple of lines of code changed running on Saturn. And we don't have Spark here right now because the Python Spark does not support XGBoost currently. And then here was random forest. This is a really, really crazy example of showing how we trained that random forest in just 1 second with Rapids. Doesn't even show up on the graph here, whereas scikit-learn and Spark were a lot slower. Now for deployments. We're going to do two things here. We're going to deploy a machine learning model as a REST API, and then we're going to deploy a dashboard as a web app. So as far as the code that it takes to do that, since we're operating in the Python native scikit-learn machine learning arena, we can just write out our model as a pickle file, and then that'll work. So and then we're uploading it to S3. So there's not a whole lot of magic happening in this function. I can show you what this looks like. It's just using Cloud Pickle to write out a pickle file, and then we're writing that out to S3 with S3FS. So now our trained model is out there on S3. And then we've got another script here for building a pretty lightweight Flask API to serve this model. So based on an environment variable that you set to basically point to that particular pickle file that we wanted, it'll pull that in, load up the model, and then it hosts this endpoint right here to do the predictions. So you'll take in the request data, we'll process the features the same way that we did for the training, and then we just do a model.predict, and then pass it that data, and then it spits out that prediction. As far as consuming this API now, the example that we're doing is doing it within the dashboard. So inside of my dashboard notebook here, we've got the prediction function. So in this case, we're hitting that particular endpoint. Based on another environment variable, we're going to know where that URL is, and then we hit that predict endpoint, send over the data, and then we get back this prediction. So that's the code that it takes. As far as deploying this stuff, I'll show you how that works in Saturn Cloud. So this is our deployments page. And if you recall, on the Jupyter page, we set up machines that had the image that we needed, and then I went in there and then I developed. I did all my code, I trained my models, I developed the dashboard. So with Saturn, all of that stuff gets saved. And so when you want to actually create a deployment, you have a thing that you did and you want to make that available. All you do is select the project you want and then put in the type of command that you would need. So if that's hosting a web app, if that's hosting an API, or anything like that. So in this case, this is the model serving that we did. So all you got to do is just run this Python script, and then that launches up the Flask API. And so if you remember, that machine had like 200 gigs of RAM and that we were developing on, and then we were using a cluster to do the machine learning. But then when it comes to serving it, we don't need a machine nearly that size. It's a pretty simple model that we're using, so we can use a much smaller instance, but it's still using the same image, and then it's using the code that was already present on that machine. And the same idea goes here for the dashboard, except in this case we're using Panel, which is a dashboard library, and then we're using that to serve it, and that's where our code lives. And then we can see the URLs where these things live. So in this case, this is the URL I would use if I want to hit the model serving endpoint, and then this is the URL that I would go to if I want to look at the dashboard, which is what we were looking at earlier in this video. And that's everything. I know I went through that really fast and I threw a lot at you, but that's because a lot happens in data science. There's a lot of moving parts. But what's great about Saturn Cloud is that it enables you to do all of this stuff in one platform. So to recap, we can build an image with all the packages that we need for our Python data science, and then launch up a Jupyter server for us to do our work. From there, we can launch clusters of machines to parallelize our computation, our data processing, our machine learning. We can even use GPU machines and parallelize across a cluster of GPUs to really, really speed up our machine learning. And then once things are ready, we can take those projects, deploy them directly via REST APIs or via a dashboard. So that's everything I have for you. If you want to check this stuff out, again, we have all the code on GitHub, and you can get started on Saturn Cloud and run all this stuff for yourself. Thank you for watching.